All right, welcome. I'm Grant Johnson, and I'd like to talk about how we added a rendering fast path to Unreal Engine and how not to break everything in doing so. A little bit about me, I'm a senior graphics programmer at Creative Assembly. I've been there for about 8 years now. I started on Halo Wars 2, then I was on Total War for a bit, and then I've spent about 5 years working on Hyenas. If you don't know what Hyenas is, it was a multiplayer extraction shooter set in space. We used Unreal Engine 4, targeting Gen 8 and 9 consoles, as well as PC. So we're going to start by looking at the problems we had getting our maps performant, and then I'll walk you through our solution called chocolate rendering. And then finally, we'll look at turning that into a modern renderer. So maps in Hyenas are called plunder ships. They're very large, sort of 500 meters by 500 meters. They're made up of rooms and hub spaces, with short connecting paths between them, usually something like stairs or a hallway. Some of our maps have multiple vertical layers with similarly short transitions, and the player can go into 0G in most areas, so we need equal detail pretty much everywhere. This amounts to about 60,000 unique instances or mesh components per map. And when you're moving around, there's no loading screens, there's no funneling. It's just a really dense indoor space that needs to be always ready. So here's an example hub space. You can see the facade that I've selected. It's just one bespoke mesh, but it doesn't include any of the internals. And then this is what a room looks like. So you can see the granularity of our modular kit pieces. I've selected 20 here, and each one of these is a base mesh and one additive mesh. So that's 40 mesh components for just these two walls. So you can see how it adds up really quickly. So you might look at that and think, why on earth are we building our levels like this? Shouldn't we just save ourselves all the trouble and just create like a single, room mesh? But there's a lot of problems with that approach. We have hundreds of rooms in our ships, and hand making them would take forever, and any edits from design would then require recreating them. So our designers wouldn't be able to iterate without an artist. We also can't reuse any of those assets, so it's puts a big burden on our streaming. And with that approach, you end up with a lot of empty space in your mesh, which is really bad for ray tracing. And we don't use Lumen, but if you want to, the documentation explicitly says not to import an entire room as a mesh. So instead, we built a custom room tool that's based on splines. Designers can iterate quickly, they move the splines around, and the tool places kit pieces for them automatically. Then to finish the room, we generate the floors and the ceilings procedurally using Houdini, and this allows our maps to always be playtest ready, which is a really important pillar of our development. And from a tech perspective, this is much more future-proof. With a mesh like this, we can adhere to the ray tracing best practices, and we can also reuse it in a bunch of locations. So we use world composition for our level streaming. Our maps get broken up into logical sublevels of a few thousand instances each. And we replace the default visibility algorithm. So instead of being radius-based, it's a tile-based pre-computed visibility. And that's just because of the overlap of all those volumes. So when you're navigating, the streaming causes those actors and components to get created and destroyed. And this triggers a load and unload of the assets when those references get resolved. So with this amount of actors and components, we saw streaming hitches. So how do we fix that? Well, instead of creating and destroying, we can just show and hide instead. So now those asset references get resolved during the loading screen. This obviously helped, but created another problem, which is memory. So having those references kept alive for the entire game keeps your assets alive. So we were using 1.5 gig of VRAM to keep all the meshes in the map loaded. And this put a lot of constraints on the art team. There's actually a second hidden cost here that you might not expect, which is that having 60,000 actors and components allocated in C++ really adds up. And this was already a problem on our server where we don't have any streaming. So when the team first switched to Unreal, the very first thing we did was check the size of actors and components. So it's about 500 bytes for an actor and about 1,200 for a static mesh component. So that's about 100 megabytes of RAM gone. And that doesn't include any mesh asset memory, any rendering memory, or any secondary allocations like the material override array, which we made heavy use of. So we're going to come back to the memory problem. We've got a bigger issue to deal with first. And for that, we need to have a look at how a component renders. So we start with a static mesh component, and that creates a scene proxy and clones any render-relevant data into it. It then goes through some magic, which we'll come back to, and then it ends up as draw calls in the RHI. So the static mesh scene proxy is nearly 2,000 bytes, which is more than the actor and component combined. And these get created and destroyed when you show or hide a component. So here's a snippet of a level streaming spike we saw in Pix. So 70 milliseconds on the game thread. The yellow at the start there is loading and unloading of levels, and then the gray is creating and destroying proxies. This then waterfalls onto the rendering thread, where we see a 130 millisecond spike, where it's going to finalize those proxies. So we made a custom benchmark fly-through tool. It's just a spline that flies a camera through the level. It's about 30 seconds from start to finish, and it produces one of these graphs. There's no characters or VFX, we're just looking at the environment here. So this is a capture from my PC in the test configuration, and the y-axis is milliseconds on the game thread. So you can see there's regular 20 millisecond spikes from streaming, with the occasional 40 to 80 millisecond spike. And then this is the render thread. So we get regular 30 to 50 millisecond spikes, with the occasional 80 to 200 milliseconds. And the largest ones there go off the top of the graph. And like I said, this is only 30 seconds. Our sessions last 20 minutes, so the overall user experience was pretty horrific. So we looked at a bunch of built-in solutions to try and solve this. We looked at instant static mesh components. They will use less proxies, but they only support a single mesh asset. And we don't really have things like forests where you would typically use these, so it just wasn't for us. We looked at merging kit pieces with HLODs. Again, it will use less proxies, but it's not designed for top LODs. So our tiling texture quality dropped. We lost a lot of asset reuse, and it comes with some CI overhead as well. We had an idea to make some custom Niagara modules. So the idea was that it would be like an instant static mesh component, but support multiple mesh assets. So the particles would act as lightweight instances, but it was going to be a lot of work with a lot of custom tooling. And Niagara was still experimental at the time, and this wasn't really the intended use case. So there was just a lot of unknowns about this. And for a while, we had an offline process that would search for common patterns and merge those assets together. So we could still retain some reuse, but it did come with an increased VRAM cost, as well as some CI overhead. So while some of these solutions did work, none of them were good enough for us to ship with. So finally, we could turn to a custom solution. So this is chocolate rendering. So anything built into Unreal, we call vanilla, and any custom rendering, we call chocolate because, well, it's not vanilla. I'll try and use these two colors throughout to help denote which is which. So the good thing about trying all those other solutions first is that now we know our data. We know exactly where the bottlenecks are, and we have a ton of failures to learn from. We're also more familiar with the internals of the engine. This was the first Unreal project for the team. And our production maps are already being made, so we have real use cases to guide our solution. But we knew that completely replacing the renderer and all of the feature combinations would just be insane. So instead, we looked for a common subset of features that we wanted to support. So you can think of chocolate as like a fast path for mesh components, similar to the animation fast path. So any unsupported components would just render through vanilla. And this gives us two big advantages. We could slowly and safely optimize by supporting new features and sending them through the fast path. And the filter can be disabled at any time, including packages. So for example, if there's a problem in a playtest, we just disable the feature flag, and you can carry on with the session. So what do we want from our fast path? We don't want any proxies. We want minimal, predictable memory overhead. We don't want the artists and designers to have to change how they work. The editor is fantastic, and we don't want to go ruining that. It needs to look exactly the same as vanilla and be able to live side by side with it. Whatever we do must be safe. We cannot break builds. We're in active development now. And we must be able to keep up with mainline Unreal. We aren't just going in with a hacksaw to try and solve this. So how can we render without using proxies? If we go back to this slide now, we can reveal that magic. So it actually looks something more like this. So a mesh component makes a proxy, which then creates some mesh batches for the LODs and sections. Those then get turned into mesh draw commands, and then each frame after the culling, it generates visible mesh draw commands for anything that was visible, and then those get turned into draw calls in the RHI. So what we want to do for chocolate is something like this. So don't create the proxies, just jump straight to caching mesh draw commands, and then we're going to submit our invisible mesh draw commands each frame, and then from there we let the vanilla RHI take care of the rest. So neutering a component is really easy. You just return null from the create scene proxy function. If you remember, hiding a mesh component destroys the proxy. And this means that everything is already doing null checks, so this is completely safe to do. But without a proxy, we need some way to represent our components in the renderer. So we call those chocolate instances. These are made up of multiple plain old data structures, and they get stored in a custom structure of array container, which is just a tuple of arrays with some helper functions. Each array is a fixed allocation of 65,000 instances, so we use 16-bit handles. And each instance adds up to just 143 bytes, so it's 9 megabytes for the entire container. This would be about 112 megabytes in proxies, but to be fair, you would never have that many allocated all at once. So we could have stored those instances in the F scene, like the vanilla proxies, but this would have made integrations a nightmare. So instead, we created the chocolate renderer. So it's a new class in a new file, so we know that there's going to be no integration conflicts. And it sits in the renderer module, so it has all the same access to the engine. We then have some hooks so that we can inject our own functionality. So things like engine startup and shutdown, level streaming, frustum culling, dispatching draw commands, that kind of thing. So you can see some examples here on the right. It's just one line of code, so it's trivial to integrate over. So next we want to cache our own mesh draw commands. A mesh draw command is a persistent representation of a draw. So things like your PSO, vertex buffers, index buffers. And this is tied to a mesh pass. So there's one of these for each mesh section of each LOD for each valid mesh pass. So whether a mesh pass is valid is determined by both the material and the component settings. So for example, you only want to create one for a decal pass if it's actually a decal material. And the code for this is spread over multiple files for all the different mesh passes. There's a lot of details hidden in CPP files and virtual function overloads. There's also some awkward dependencies to things like the view constant buffers. Thankfully, that has been improved a bit in UE5, which is nice. So we could have tried to retrofit our changes in there, but we instead just duplicated what we needed and untangled it a bit into a unified solution we call the draw builder. And this works for any mesh and any mesh pass. And my general advice is to always duplicate and never modify. There's obviously exceptions to this, but it's been working really well for us. It's just so much easier to integrate engine updates. You just have to be vigilant to see if anything changed in the original. So it really helps to leave paper trails. So just things like, this function was duplicated from, this function in this file. So caching mesh draw commands is a big part of what makes proxy creation so slow. So like this 56 millisecond spike we saw on the render thread. And our unified draw builder doesn't fix that, but it does give us full control over when it happens. And since we know all of our combinations at level start, we can just fill a cache during the loading screen. So then the key into this draw cache is just a few pointers, a mesh pass enum, and some flags. So now when a component is streamed in, we just do a lookup with the key and we're ready to render. So the last step is to create and submit visible mesh draw commands. So if a mesh draw command tells you how to draw, then a visible mesh draw command tells you when to draw. So there's a list of these for each mesh pass, and they get generated each frame after the culling. And they get given a sort key, which determines their order within their pass. So we have a hook for view culling, where we divide our active instances into groups of 512. We spawn a task in the task graph for each group, where we do frustum and umbra occlusion culling. And if it's visible, we create a vanilla visible mesh draw command. And that gets stored in a task local packet. And then when all the jobs are done, we merge them together. Then later in the frame, these get collected by one of our hooks, where we just mem copy onto the end of the vanilla arrays. So there's one more thing we need to fix now that we don't have proxies. So the GPU scene allocates primitive data for things like the world transforms. So we need to provide all that ourselves now. So we just append our chocolate primitive data at the end of the vanilla buffer. The vanilla proxies get given a primitive ID, which is just an index into this buffer. So we need a fake ID, which is just the vanilla primitive count plus our chocolate instance index. And that gets passed through the visible mesh draw command, so now all the existing shaders can access our chocolate primitive data. There is one more problem here, which is that the primitive data is really bloated. It's 576 bytes per instance with a fixed layout. So there's tons of waste in there, especially for static level geometry. So with our 60,000 instances ready, this is about 33 meg of VRAM just gone. So we will come back to this, but it's fine for now. So we could actually stop here. That is all you need to render without a proxy. But we're wasting memory on actors and components for features that we're just not using. So if we go back to this graph and expand up, you can see that components belong to actors, and in this case, they belong to levels. But we really don't need these two, so let's just go ahead and remove them. And instead, we're going to store a list of instance descriptors on each level. So these get used to initialize our chocolate instances the same way that a component initializes a proxy. So each level is going to build a list of these descriptors, extracting everything it needs from any valid static mesh components, and then they get serialized alongside the level. It's a very lightweight descriptor at just 120 bytes. It's essentially a mesh, a transform, and a couple feature properties. And a reminder, actors are 500 bytes and mesh components are 1200 bytes. So our levels can have thousands of these instances, and we want to be able to perform efficient bulk operations for things like showing, hiding, or moving. So our renderer works on chocolate batches. You never actually create instances directly. So a batch allocates a contiguous range of instances from our structure of array container, and then they get initialized all together with the serialized instance descriptors array from the previous slide. So our level streaming is now just a call to show or hide on a batch. So we're not using the actors and components outside the editor anymore, but they still exist in our packages. So we need to remove them during the cook. And you do that by just destroying the component when you're cooking the level. And if an actor has no valid components, we can destroy it as well. So our 60,000 instance descriptors is about 7 megabytes. So we've saved 95 megs of RAM by removing those actors and components. There is a downside to this though, which is that we can't fall back to vanilla in packages anymore. So you need to make a new package with the feature disabled. But in practice, this was fine. Chocolate was stable enough by this point in development that we never really needed to do it. So static mesh components also provide a collision body through the provide collision through a body instance. So we need to replace that too. So when we extract our instance descriptors from the level, we also extract body instances. And there's one of these for each component. We then insert a new multi-body collision actor into each level, which is going to recreate all of those body instances for that level. We then set the multi-body overlap bool to true and set the instance body index so that we can identify them in callbacks. We've also broken texture streaming. This effectively works by calculating the size of your component bounding box in screen space and requesting the appropriate MIP level. So this expects a matching primitive component in the component array, which we don't have anymore. There are some fallbacks though, so you won't notice that this is broken straight away. But we don't want to add a second array for our instances. It's just going to be too many engine edits. So instead we use tagged pointers. So the first couple bits of a pointer are available because of alignment. So we're going to take the first bit. So we replace the primitive component with our chocolate tags pointer, and that just stores a uint64, which is either the address of the component, or it's the chocolate instance index shifted up by 1 bit. So now the first bit indicates whether it's chocolate or vanilla. And then we take advantage of C++ casting operators and implicit constructors. So as far as vanilla is concerned, it's still a component. We don't have to make any modifications. And now we can just insert our chocolate instances and bounding boxes with minimal engine edits. So we made the decision early on, in order to save time, that we weren't going to allow editing while chocolate was enabled. So it's off by default in the editor with a shortcut to enable it. But once you reach 100% parity, the only difference is performance. So we added these on-screen ice cream cones to differentiate the two modes. And these are also there in development packages, which is really helpful in bug reports. And yes, I made those myself. So we then have a traffic light system. So when you select an actor or component, You will either see a green light for a passing filter or a red light for a failure, and a list of reasons why. We also have a map check that does a full status report, which is really useful when evaluating whether or not to support new features. And we aim for something like 90% coverage, but in reality, it's more like 75%. So Chocolate was designed for static environments, but movable props were a case where it was worth adding support for a feature in order to improve our coverage. So we have these large zero-G props that just transition up and down, and then we have your typical small physics props, things like glass bottles and coffee cups. So to add support, each game thread frame stores movement requests in an array of instance indices and their new transform. And this is triple buffered as the render thread is going to consume that update. We then added a new static mesh component, which inherits from the vanilla one. And all we did was overload the onUpdate transform so that we could automatically send those changes across. This does mean that we can't do actor and component removal for these though, since we're relying on that callback. So here's our original benchmark for the game thread. And overlaid in yellow is Chocolate. So there's still some spikes, but it's a lot more stable. And the way to reduce those spikes further is to improve our coverage. And this is the render thread. Again, yellow is Chocolate. And again, you can see we've reduced the spikes a lot. It's a lot more stable. There's still work to do, but it's a much better experience. So with all that done, have we achieved our goals? We've removed proxies, and we cache mesh draw commands during the loading, so we've significantly reduced our streaming hitches. We've reduced the memory overhead of our show hide streaming by removing the actors and components, and we solved it on the server too, since they get removed on both. Our designers and artists are still using actors and components in the editor, so nothing has changed there. We filter actors and components so that only those that can achieve parity get a taste of Chocolate. We didn't break vanilla, we just augmented it, so we work side by side. We used feature flags to ensure that we never broke a build. And we made surgical edits to the engine, so our integrations are still straightforward. So we've solved our initial problems, and we could have shipped this, but we still have a bit of time and some outstanding problems that would be nice to fix. So we have tons of small draw calls. Our primitive data is still bloated, and our mesh assets are still always loaded. So let's start with the small draw calls. They cause a lot of overhead on the render and RHI threads. So we first have to generate and sort those visible mesh draw commands, and then record those into an RHI command list, and then translate that into a graphics API specific command list. And remember, these are unique instances, so we can't rely on any of the built-in techniques like auto-instancing. So what if we moved all of this to the GPU with a modern renderer inside of Chocolate? So we looked around for a bit of inspiration, and these three talks provided it in droves. GPU-driven rendering pipelines, optimizing the graphics pipeline with compute, and rendering the hellscape of Doom Eternal. These are all amazing. If you haven't already, please go read them. So to modernize Chocolate, we're going to need to add compute culling and merging of our draw calls. We're going to need to switch to meshlets or clusters, and we might as well stream them. We need to add bindless support in order to draw our merged instances correctly. We need to minimize the number of material permutations through the use of dynamic branching. And we still don't want any surprises with our memory usage. A little bit more terminology. All the rendering in the first half I'll refer to as traditional, and what we're about to discuss I'll call modern. So we know that not everything is going to go through this modern path, so we still need to support both. So we have another filter for this. It's a much simpler one though. It's just, does your material support the modern path? So the blue shows the existing traditional path, and the new modern path in green. So after frustum culling, we're going to create render items, and then we're going to issue RHI calls to do the compute culling and draw the results. So here's an example of the filtering with a in-engine debug view on the left. So red is traditional for things like transparents and animated emissive strips, and then green is modern. So the majority of our environment is going through this path. So a Chocolate render item is essentially the same thing as a visible mesh draw command. It's a lightweight, sortable representation of a draw. But the vanilla draw command has a bunch of stuff we don't need. So our render item is 5 times smaller. It's just a sort key, the instance it came from, the LOD to render, and an index to some draw info for that LOD. So now our frustum culling tasks are going to generate either a render item or a visible mesh draw command. We then group these render items based on their mesh paths and material, and each group is going to generate a compute culling and indirect draw pair. And there's a maximum of 20 of those 20 of those pairs per frame. So we can't have a huge amount of materials in order for this to work. So I just want to quickly go over our approach to materials. So we came from custom tech with handwritten shaders, so the material graph was a bit scary. So we were quite firm with enforcing a core set of master materials, so our artists only make material instances. This comes with a lot of benefits though. We have a significantly more consistent look. All of our textures are packed in exactly the same way. We have a lot less PSO compilation. Our traditional path is a lot faster because we have less PSO changing. And our modern path just wouldn't have been possible without it. So we only have 2 modern materials to choose from, the environment and mesh decals, and neither of them use any static switches. So we do have bespoke materials for things like emissive strips, mask surfaces, and our augmented reality billboards, but those just go through the traditional path. We don't want to be spinning up compute shaders for just a couple meshes. So back to our compute culling. The shader is fairly straightforward. It's a one-dimensional workgroup of 256 threads, and each thread just processes 1 triangle. It's always triangles of the same mesh, which means you're potentially processing degenerate triangles whenever a mesh doesn't perfectly divide by 256. 256 triangles per workgroup is quite high. We did try smaller sizes, but we ended up settling here. And the reason for that is that we don't have a sorting pass after culling. So the smaller your size, the more randomized your output is, which hurt our rendering performance. So the shader first reads the triangle vertex positions. It then does backface culling, and then occlusion checks against a high-Z pyramid texture that we build from the umbra depth. We then do small triangle culling, and then frustum culling. And then any visible triangles append what we call indirect indices to an output buffer. And that's just a 12-bit draw index and a 20-bit vertex index. And each triangle is going to write 3 of those. This then gets consumed by a matching draw indirect call. So the culling output buffer gets bound as the index buffer for the draw. So we receive our packed indirect index through the SP vertex ID semantic. We then unpack that to get our draw and vertex indices, and use it to load a small structure of draw-specific offsets called an inner draw. So you can think of it like a draw within our merged draw call. And that gives you access to things like the primitive data and the vertex fetch tables. So we load the vertex fetch table, which has our offsets to the vertex streams. Then we load our vertex streams, and then we patch that into the vanilla shader. So there are a few indirections along the way here, but the gains we saw were well and truly worth it. And this is all done within a custom vertex factory, so we're still using material graphs. So here's some examples of the culling phases. So backface culling first. If we freeze the rendering, you can see the triangles behind get removed. And again, with frustum culling, anything outside of the frustum got removed. Occlusion culling, you can see the Roland 808 occludes the triangles on the robot's body. And then small triangle culling, we move the camera far away, and you can see all the triangles that would have been sub-pixel in that original view have been removed. And here it is in a real scene. So we start with 778,000 triangles. We enable backface culling, which removes 340,000 triangles. Frustum culling removes 93,000. Occlusion culling removes a further 120,000. And then small triangle culling removes 65,000. So with all of this enabled, we've gone from 778,000 to just 160,000, which is about 80% of our triangles. So we originally had a meshlet culling phase before the triangle culling, and this meant that we needed proper meshlets, which we generated with the mesh optimizer library. And that just groups triangles that are spatially coherent and have a similar facing direction so that they can be culled together. We ended up ditching this though, and went for a really dumb clustering where we just take runs of 256 triangles. And there's a couple reasons for that. Our scenes just don't have enough triangles. So the barrier between the two compute passes causes an occupancy valley, so it's actually just faster to let one compute shader process more triangles. And our meshes aren't organic. We're all hard surface models, so it's not very common to have both spatial coherence and a similar normal. So we ended up with a ton of degenerate triangles, which meant we needed a smaller meshlet size, and it takes us back to that randomization problem from before. So all of our data access needs to be bindless now. So we can add RHI support for bindless textures, that's fine. But we also need to be able to access all of our buffers. So things like our vertex data, primitive data, and shader constants. So we opted for a unified buffer approach, where we just allocate one big buffer from the RHI and sub-allocate that ourselves. So our shaders just have offsets into this one buffer. So we call this buffer the device memory. It's just a fixed size, 256 megabyte buffer, and it uses a straightforward free list allocation strategy. Our users get returned a handle with the byte size, offset, and generation. And this is accessible in the view shader parameters, so pretty much every shader can access it. The device memory isn't accessible by the CPU though, so we need some way of getting data into it. And for that, we wrote a small 32 megabyte staging ring buffer. And like the device, users get returned a handle with the byte size, offset, and generation. And then we use a compute shader to copy from staging to device memory. So with bindless rendering, you have a lot of offsets and indices. So we group these into two tables. The first is the vertex fetch table. So this has offsets into device memory for the streams, any compression data, and flags. And there's one of these tables for each streamed in LOD level. Then we have the material fetch table, which has the texture indices. So these are 16-bit with a maximum of 8. There's some dynamic branching switches, as well as a handful of common parameters. And again, it's a fixed layout, and there's one of these for every material instance. And we actually extract those from the vanilla material instance, so our artists are still using the regular editing workflow for this. So now we can go back and fix our primitive data. If you remember, the vanilla structure is 576 bytes per instance, and this is the list of all the properties it has. We shrank that down to 112 bytes. Anything in green is what we kept, and we also added a couple of our own parameters as well. But we just don't need things like the pre-skin local bounding box for a standard environment asset. And that took us from 33 megabytes down to 6.4. So a chocolate batch allocates a block of device memory for its primitive data, and then it uses staging memory to do either a full or a partial update. All the vanilla material shaders funnel down into this one get primitive data call. So if you remember, we pass a 32-bit primitive ID to the visible mesh draw command, and this is where it ends up. So we hijack this to instead pass a byte offset into our device memory for where our primitive data is. And from there, it's easy to just load and patch our own data and put it into the return value. And any of the properties we don't support, we just set to a sane default. So bindless texturing isn't supported by vanilla, so we had to add it ourselves. The implementation is kind of awkwardly broken in two, but it was the best way to support multiple platforms. So this first half gets duplicated for each RHI that we support. So for D3D12, we store an array of 4,096 descriptor handles on the device, and this is our ground truth for what texture is in what slot. We then append a copy for each frame onto the end of the global view heap. And since that's shared with vanilla, there's no heap swapping, so we can efficiently mix vanilla and chocolate draw calls. We then have a ground truth version counter and a copy of that for each frame. So each time a texture slot changes, we just bump that number, and then at the start of each frame, we compare the versions and do a copy from the ground truth to the global view heap if required. And to access that in our shaders, we had to modify the root signature. So we added a new register space and put our SRV array there. And we also added 2 root constants that we use for some draw offsets. So then the second half sits up in the renderer. So we added this bindless API where you register a U texture and you get a chocolate texture handle back. And the index of that handle maps directly into the descriptor array, so you can use this to build your fetch tables. And all of the communication between these two layers is done via RHI commands. To add texture streaming support, we just added a chocolate texture handle to the RHI texture reference object, which is just a stable object that can swap out what texture it references. So when that reference changes, we just update the bindless ground truth array, and now the two are kept in sync. So bindless material support is honestly pretty rough, but we only had 2 modern materials and no artist authoring, so it was definitely the way to go. So we added these 2 new material usages, one for traditional and one for modern, and these are available as a preprocessor define when you're compiling that permutation. So we have a custom code node that implements a switch using that compile time define. So if it's the modern permutation, we'd load the material fetch table, grab our texture index, and sample from the bindless texture array. For anything else, we just return the fallback, which in this case is a texture sample node. And this means we have a single material which works for both bindless and traditional draw calls. So we also need dynamic branching, which is kind of tricky in material graphs. So what we ideally want is that the branch has the code scoped inside of it. But the material compiler effectively flattens your nodes down rather than building a hierarchy. So the built-in if node is going to evaluate both A and B, and then just mask the output, which isn't going to generate a branch. So we can make a branch ourselves in a custom node, but we end up with the same problem where A and B get evaluated first. But this is actually okay though, because what we discovered is that if the compiler generates a branch, it's going to reduce the scope of those expressions for you. So we just added a branch hint to help ensure that that happens. It's not a great solution. I do have an idea for how to add proper dynamic branching into the material compiler, but it's good enough for now. So we're still sharing meshes with vanilla, and they don't have any meshlet or cluster support. We could have added it, but we chose not to. And one of the reasons for that is we knew we wanted to do some unrelated optimizations. So instead, we created the chocolate mesh. This was originally a standalone asset that was generated from the vanilla asset. But because it had to be kept in sync with vanilla, it was just a nightmare for artists, as well as for CI. So instead, we store custom render data inside the vanilla mesh. And we discovered this is actually how Nanite does it too, which is always a good sign. So now we have a bunch of duplicate data in the meshes that we don't want. So at cook time, we analyze how they're used and only cook what is needed. This also meant moving our traditional path over to using chocolate meshes. To add streaming, we just use a pool inside of the device memory. So it's a fixed 230 megabyte block, which is almost all of our device memory. And this gets shared by all of the meshes, which is really important because now our shaders can access any mesh with just an offset. Okay, so let's take a look at a GPU capture for how this all comes together to render our service core here. So this is a wireframe from the first compute draw pair, and it covers almost all of the environment. It's 1,800 inner draws and 5,600 clusters. We then render the 0G debris, which is about 4,000 inner draws and 4,000 clusters. And there's actually a limit on how many triangles a compute draw pair can process. So this one here is just overflow from that first draw. We also rendered 960 mesh decals with 1,500 clusters in a single pair. And it's worth noting that there are a couple more minor base pass and mesh decal pairs that I've not shown here, but the majority of our G-buffer has just been filled by 4 compute dispatches and 4 draw calls. This would have required nearly 7,000 traditional draw calls. So the amount of work that we've removed from the CPU is huge. It's also worth noting that the gains on the GPU are not that big. So our biggest GPU win came from the master materials, not from merging draw calls. In just drawing, we are faster than traditional, but if you factor in the compute culling cost, it's about on par. As it turns out, trying to beat the GPU at its own game is really hard, especially when our traditional path is the best possible case for a GPU. With almost no PSO swapping, it can just crunch through all those draw calls. And this isn't to say, though, that we ran out of runway for optimization, but just that the GPU was never our bottleneck, so being on par with it was sufficient. The big difference here is the CPU setup cost, and that's the bottleneck that we wanted to fix. So have we solved our outstanding problems? We now merge draw calls on the GPU, and our CPU setup has been greatly reduced. Our primitive data is 5 times smaller, and our meshes can now be streamed. So they're no longer always loaded, taking us from a 1.5 gig fixed cost down to a 230 megabyte pool. So having this modern path unlocked a ton of features for us. We have a new bindless tile-based lighting path. We added DDGI and used bindless for the probe-atlas sampling. We have 0G debris volumes, which is the only feature that's actually exclusive to chocolate. There is no vanilla parity for it. So their physics is simulated on the CPU, and then we use just about all of the modern features to render them efficiently. And our art style relies heavily on decals for things like bolts and paneling. And as you saw, these are all merged and drawn through the modern path. So we also integrated Deer ImGUI directly into the chocolate renderer. And with this, we can now inspect the texture streamer, the RHI, our bindless ground truth, our chocolate vertex streamer, and our draw cache. And I really wish we did this earlier. It was so valuable once we had it. So when Nanite was announced, we got a few awkward questions like, hey, isn't that kind of what we're making? But hopefully you can see now that we're not trying to solve the same problem, despite having similar looking debug modes. Nanite, at least in my opinion, is focused on cinematic triangle counts, whereas Chocolate, we're focusing on large numbers of unique instances. And Nanite still uses scene proxies, so it's going to suffer from all the CPU issues we've discussed here. With that in mind though, what about a chocolate-flavored Nanite? I don't see any reason why not. We've got a ton of ideas for the future. I'd like to support skinned meshes. It's a little bit tricky as we need to skin the triangles before culling, but also because true meshlets work really well here, which is a different requirement from our levels. I'd like to support way more instances. We hit that 65K limit really quickly with like 60,000 for our levels and then another 10,000 plus for debris. This means that not everything is as modular as we'd like it to be. It's not a trivial change though, as a lot of things are relying on 16 bits for those indices, so some of that needs to be rethought. I'd also like to add editor support. So having multiple paths was a pain. Things like actor removal not being present in the editor or in standalone. I just want to unify all of those paths and have chocolate always be on. And I'd like to move more to the GPU. So having a full hierarchy of culling with something like persistent threading and a multi-in, multi-out queue, so that we can go from instance culling all the way down to sorting and drawing our triangles. And with this, the CPU becomes even simpler. A few things I'd like you to take away from this talk. A slow takeover is a very safe and powerful way to add new tech to Unreal, especially when you're in the middle of production. You should try and duplicate or add engine code instead of modifying wherever possible. You just need to be vigilant when updating to look for changes. And this last one's kind of obvious, but custom solutions to your actual problem massively outperform the generic one. When we present these results internally, we usually get asked if we should try and give this back to Epic in some way. But a big part of what allows us to be fast is that we only support like 1% of what vanilla can do. But that's all we actually need. So this work was a joint effort between myself and Jose Sanchez. And of course, it wouldn't have been possible without the contributions of Simon Moose, Alex Charwood, and Alessandro Monopoly. Thank you.